Hello, dear listeners. Hello, everyone. My name is Farid Yagubov, and as an independent researcher studying certain aspects of neurobiology, neuromorphic technologies, and programming, I would like to talk about a new approach to developing real machine intelligence. In this presentation, I will explain advanced neuroscience technology, which goes far beyond current CMOS transistor microelectronics. And as we know from professional scientific literature, brain activity is localized and can sense only 10 watts unrest. And under increased load, when the body solves previously unseen non-standard problems, the activity of the nervous system can increase up to 25 watts. Neurons are not just a computational system or similar computer architecture, as it is represented by the overwhelming number of modern engineers and programmers, and several properties in the brain can be modeled even at the level of electronics and lithography processes, let alone algorithmic approach. And so let's move on to the next slide. Given some of the limitations of electronic components as early as the 60s, many atoms were made to move beyond the static transistor architecture. Semiconductor computing, unfortunately, has persisted to this day, and the silicon architecture that has continued to limit computer technology for 60 years is due to quite a few reasons. The memristor that was proposed by Leon Chua as a theoretical model in the 70s is one of few attempts to revise the transistor architecture. Out of the first experimental observations of the existence of memristor properties were made by the great scientist Sir Humphrey Davy some 200 years ago. Besides, the closed hysteresis loop exists in many dissipative objects, and even in organics. But the full-fledged physical development of Leon Chua theory was realized only in 2008 years under the leadership of Richard Stanley Williams in the laboratory of Hewlett-Packard. His group described in detail the mechanism of hysteresis and the presence of memory in one type of nanoscale oxide material, titanium dioxide. Later in 2013, Richard Stanley Williams' group first realized a neuristor from memristor components with a mode phase transition of niobium dioxide and standard capacitors. The current defined types of oxide memristor that are the core of the new neuristor computing architecture can mimic most of the physiological processes of biological neuron. And most importantly, this type of device has a huge potential in creating a real thinking machine intelligence. Let's move on to open source video fragments. In this video, the authors of memristor technology demonstrate a real example of new computer architecture and confirm the advantage of neuromorphic intelligence based on neuristors in solving non-standard tasks.
You are going to build, one of you who is going to build the world's first real brain-like computer, okay, or anybody else, and I can assure you it's going to be made of memristors, okay. There's no other way that I can think for 100 years from now. I can tell you that there's no other way that I can imagine, okay, because you got to have something so small, okay, that's non-volatile.
Now, the way a memristor works, we have a prop shown over here that's blown up about a factor of 10 million times bigger than this wafer. And what we have is at every single intersection point, we have 1 bit of data being stored. And the way it works is by just applying a small voltage pulse, we can create or break connections, and that way either store a 1 or a 0. And this is a very small technology and a very fast technology. The other benefit is that we can actually add multiple layers. And so that is what's illustrated in this prop, where we've actually shown that you can actually stack 4 layers of these memristor arrays, and that way quadruple your data density. With this interface, we can write a 1, or we can write a 0, and by monitoring over here, we can see the result of that. So here we write a 1, and indeed it goes to a low resistance, or we can write a 0, and it goes to a high resistance. And it'll store that data indefinitely with no power. So we're focused here on brain-inspired computing. The goal is not to replace humans, but to take advantage of some of the tricks that brains use. And brains look very different than modern digital computers. Instead of the separated memory and processor that goes through sequentially and does an instruction at a time, brains instead look like these vast networks of neurons with extremely dense interconnections called synapses. And the kinds of operations that brains do, they do at thousands of times less energy per operation than digital computers. So we want to take advantage of some of that. We're also taking advantage of a technology that's been in development and research at HB for a number of years, memristors. So there's three parts to our work. Number one, we're mimicking this architecture that I just talked about, this vast network of interconnecting neurons and synapses. We're doing that with the memristor technology. Second, we're actually doing all of our computation in those memristor arrays directly. So this way we're avoiding fetching data, which is very energy consuming and time consuming. Instead, we're bringing all of the computing to the data directly. And so that's a big deal. Third, we're actually reproducing the key operations that brains appear to use, which is matrix operations. A whole lot of very simple multiplications and additions.
You're actually trying to collapse all of this system down into a single chip, the one that we were just seeing.
Yeah, that's right. We can scale all of this hardware down to the size of roughly this chip right here.
It's incredible.
First, you're using a physical process, Ohm's law, to do a multiplication, and instead of relying on digital technology where we're having to pull not only we have to pull all the numbers into the processor, and then we have to push the result out. And here, once you have set that value, it's always there. You pay that energy charge one time. You never have to move that weight again. And then you can use it over and over and repurpose it. So when I think of that deep embedded system, not just the exascale, but at the complete other end of the spectrum, that deep embedded system in a spacecraft, in a deep embedded system at the bottom of an oil well, something that is so hard to get to, you have this ability for this neuromorphic and neuroplastic system to be constantly changing, adjusting, learning, and be that incredibly efficient engine. So I think that's what's so amazing, that sustainability of this technology.
So this might be a little bit out there. Current incarnations of something like this, if you look at IBM's Watson, it has storage that it pulls from existing data. So
Yes.
That's how it's able to pull up with answers. Are you thinking about possibly putting something in this to where it can ask itself questions? As opposed to, like right now with a SQL Server data system, you ask the question, it caches the answer, so if you ask that question again, it can get the answer back.
Yeah.
But if you were to put something in like a Fermi equation, anything like this, and it can store it and give it itself the ability to just posit through all of these different things so that the answer could already be there?
So either you have read Turing's Cathedral, or you are very prescient, because there's an entire chapter in the book that talks about some of these types of issues. Let me say, first of all, that I am not a big fan of sentient machines. I don't want a sentient machine, and at least the present understanding in the field is that in order for sentience to exist, an entity has to have a model of itself in its environment. And my view is I want to deny any machine that access. I don't want machines to have models of themselves in the environment. And so at some level, I don't really want the machine asking originating questions. But what I do want it to be able to do is, when it is asked a question, to then be able to follow a sequence of inferences and propagate out into a system and literally realize, again, have I seen this before? Essentially recognize. Is it something that I can I guess an answer, or do I have to go ask, do essentially a web search and see if there's something out there that's been doing it, and so that's sort of keeping things within a shell, shall we say, of denying the machine a model of itself in its environment. Once it starts asking questions on its own, then there are certain aspects of it that I'm not comfortable with following that train.
Quick follow-up.
Yes.
If it's supposed to follow a logical procession to understand and find this answer, couldn't the next logical question be, I wonder what his next question should be?
Well, let's put it this way. You are asking some absolutely front range questions on the bleeding edge of information science and computing, and you're absolutely right. I mean, that is a potential outcome, and I think that what we want to do is, my own view is that I want to proceed cautiously. I mean, in George Dyson's book, he actually has a little chapter in it, and what he says is that if computers become sentient, we won't know it. The entire World Wide Web could become sentient in a microsecond. The transition from non-sentience to sentience could happen so rapidly, and the machine itself, the entire system, could figure out what the consequences of us learning that it has become sentient so fast that it would never let us know. Okay, so we're playing with fire here, right? I mean, you can get burned, but on the other hand, if we hadn't had fire, we wouldn't be where we are today. So this is an issue. Go in with your eyes open, understand what the consequences are, and deal with them up front. But those are great questions you're asking.
As can be seen, at the end of discussion, one of the authors, Rich and Stanley Williams, is primarily focused on creating new control mechanisms for machine intelligence. This stage is extremely important because a self-organizing adaptive computing system will be capable of very intelligent actions that will be difficult to control. Alright, what modern neuroscience consists of? Memristor as the 4 passive element and as a 2-terminal NAND device based on complex oxide materials, has adaptive stochastic properties, analog signal processing, as well as built-in variable resistor memory and sensory function in addition to energy independence. The memristor properties of the capacitor have an additional set of advantages in short-term charge accumulation, or more precisely the accumulation of the experience or perceived events and the computational memory of incoming signals. A MEM diode, or MEM capacitor, along with a sensory memristor, with integrated variable memory, is the core of a complex neuristor circuit that can generate and modify entirely new non-repeating multimodal analog signals. Adaptive spike and oscillator neuristor architecture based on innovative memristor and capacitive elements is a promising direction to the creation of new computing technology capable of synthesizing new information. The Hodgkin-Hughes math model of the 1950s, which was experimentally studied on a giant squid axon, has no less than 20 physiological parameters. In principle, almost any scientific paper related to the creation of a biosimilar computing system based on algorithms or electronic simulators are based on the Hodgkin-Hughes model. With hardware and software adaptation, this model doesn't give the desired results when solving spontaneous problems in real-world conditions. Even in the early 60s, Hewitt Crane, author of Neuristor Electronics, realized that to transfer the math Hodgkin-Hughes model to a new hardware architecture, new semiconductor components will be required. He used a 4-level Shockley diode for experimental decision, hardware emulation of the Hodgkin-Huxley model using static electronic, quantum, and optical components is resource-intensive that end to modeling real machine intelligence. In addition, recent research in neurobiology, pharmaceuticals, and molecular materials in the field of neuromorphic technology has shown that neuronal as well as XN.O activity doesn't operate in as fixed a manner as Hodgkin and Huxley described. It's very fortunate that even in the field of neurobiology, some laboratories pay very little attention to detailed study of the phase change of the modulated signals that simulated neuropeptides and neurotransmitters in each synaptic vesicle. In reality, this neurobiological enigma is a potential key to more plausible modeling of neurosystem based on novel memoristic components that go beyond excited materials. Given that there are approximately 600 types of variables per vesicle, and more especially the coexistence of huge number of transporters, amino acids, neurotransmitters, neuropeptides, and receptors that encode that and reconfigure connections in an ultra-complex manner, it becomes clear that such an architecture can be emulated by nanoscale electronic semiconductor elements. The limited physical, math functionality, and material science of transistorized components that share computation, memory, and sensing properties are completely incitable for adaptively non-standard tasks. Digital, optical, and transistor architectures are flight direction of the next generation computer architecture. Attempts to improve the architecture of neuristor devices from the 60s to early 2000s were unsuccessful due to the limitation of knowledge in material science and nanoscale lithography technologies. After years of searching and synthesizing complex adaptive oxide materials used in many applications, nanoscale scaling and decision of new neuristor architecture became possible. Typically, a neuristor microprocessor is decision is crossbar architecture with neuristor on the periphery and memristor in the middle that mimic the physiological functions of neurons and synapses through which complex coded signal travel. The most advanced technology is the interdisciplinary research of several institutes of technology under the Air Force Office of Scientific Research Program. The cerebral-memory research program, authored by Alan DeLittle and Louis Piper, has demonstrated a niobium pentoxide (MDOT) and lithium niobate-based wide-sensitive memristor element. Most interestingly, the lithium acts as an ionic computation reservoir that surrounds the memristor elements and allows analog signals to flow very chaotically and autonomously without additional programming. This approach is in stark contrast that used in modern microelectronics, where primitive binary information flows along limited signal paths. The full autonomous activity and self-programming of neuristor components is the most innovative advance in the new functional computer architecture. Integrated analog processing, memory and sensing allow neuristor circuits to instantly identify targets, extrapolate it, and synthesize new visual information. The most important thing that distinguishes this innovation from the current digital algorithms is the instantaneous response to stimulus and autonomous modification of accumulated experiments with self-organized behavior in complex situations. All these analog functions of a small sensor are performed in real time when solving non-standard visual tasks, which is beyond the capabilities of even many cloud supercomputers. After the end of World War II, the transistor as a free-terminal device was probably a very innovative solution for the limited computer functionality and the possibility of further miniaturization. The information content and amount of data in the computer architecture of the 1950s was very small and did not require a complete revision of the element base of the old computers. In addition, the lack of advanced electronic beam lithography in the 1950s limited the emergence of new microelectronics elements. Beginning with the development of large-size electron tubes and ferrite cores, computer architecture remained limited throughout the 28th century. Despite today's nanometer scalability, in lithography, transistors initially lacked multifunctional properties given their electronic physics. At the beginning of the 21st century, the situation has changed dramatically and the partitioned digital architecture with processing memory and Boolean logic doesn't correspond to modern functionality. The development of real neurocomputers will require revision of the whole spectrum, from material science to complex applications. And so, now let's go to the real advances in computational material science. 15 years ago, neuromorphic microprocessors were basically designed as a crossbar architecture with the two components in vintage computer chips. The first is a memristor neuromorphic, and the second is an oxide memristor. Recent advances demonstrate new possibilities. It turned out that with the help of new vanadium dioxide can be combined both memristor and memcapacitive function in single nanodevice, thereby reducing the size of microprocessor. In addition, 4 years ago, Sir Bajit Banerjee, along with Richard Stanley Williams, developed the latest sensing metal insulator from fast vanadium pentoxide. Apart from memristor properties, diffusion of copper in this material creates power and oscillations, which makes such a device very sensitive to multiple stimuli. The application of such a device in a neuristor circuit can set new adaptive functions, but the main achievement is the supermunction functionality of a new molecular memristor based on a rare ruthenium complex with as aromatic ligands. Complex redox process in this type of material allows to imitate not only ternary memristor and binary memcapacitors, but also 71 logic operation that can be reconfigured in real time, which is impossible even the complex oxide materials. The characteristics of this material are very unique, and the best part is that the device is reproducible and durable compared to oxide as well as silicon materials. The unique molecular device is worthy candidate for the development of next-generation neurocomputers. This invention is attributed to Indian authors such as Sritosh and Sribhat Goswami. Richard Stanley Williams is currently a professor of computational electrical engineering at the University of Texas, and the director of the Reconfigurable Computational Architecture Research Center at the Department of Energy, along with Sritosh and Sribhat Goswami. The research group in the Department of Energy is trying to introduce and find applications of molecular neuristor technology in new areas. Now, it's necessary to point out the current limitations of algorithmic approach and stagnation problems in the field of microelectronics. To begin with, let's talk about the primitivization of thinking of modern users of AI services. The fact is that static queries and resulting answers of machine algorithms are absolutely predictable with the framework of math calculations and static electronics of supercomputers. Machine algorithms can indeed act as quality tools in performing very narrow tasks, but no more than that. Fitting models to the result of digital neural networks is an indication of the primitiveness of the architecture of modern computers and the possibility to go beyond the preliminary limited solutions. No advances over the last 50 years in computing are either fiction or optimized version of new algorithms. Even some minor computing technologies of the United States and Soviet Union are hit of modern digital computers in terms of advanced architecture of 1970s. Demonstrating certain traits from modern AI models is a primitive attempt to make big money. Basically, recent advances in AI services concern matrix computing convolution networks, encoders, decoders, diffusion models, and large language model transformer architectures. Such architecture is not only deterministic, but also poses a lot of challenges in terms of energy cost in big data processing. No matter how much the block architecture of neural networks and a static architecture of computers are improved, they will not be able to approach real biological systems due to the limited electronic element base. Integration of all modern algorithmic approaches with limited transistor logic are analogous to dead brain, postmortem brain. High-level programming languages are only a logical description, a program functionality, not a physical reconfiguration of electronic properties. I myself have had the opportunity to see the computational limitations of AI models by applying the simplest editing of scanned 19th century portrait. By minimally changing the input data of the image, modern supercomputer-based AI models cannot even approximately determine what's in the picture. It's also known that ChatGPT and many other similar AI services have already primitive search query and fixed answers. Modern AI achievements published by many companies are just a bait for earning additional funds. And if we take into account that the overwhelming number of users using such services as ChatGPT and Sora, to put it mildly, are not competent in their field of activity, that we can confidently say that such thinking is tantamount to the instinctive hormonal intelligence of insects. Algorithmic type of users or bloggers, whose intelligence is only an imitation of other people's abilities to repeatedly praise the achievements of modern AI algorithms, which is comparable to a new religious movement. This continuous primitivization of thinking of mediocre participants of AI business services substitutes of real biological intelligence for instinctive insectivorous thinking with the help of modern digital computers. Despite the many limitations of modern computer technology, there are some advantages. The transistor architecture of modern microprocessors can well fulfill industrial and certain social problems. Given large databases and multi-level algorithmic libraries, finite automata can be adapted to perform certain actions with the certain manipulations. Graphical tensor computations at the level of parametric operations, AI services, and multi-agent AI with great difficulty solve in an invariance problem if it concerns non-standard tasks. The major advances in modern computers are nanoscale microprocessor lithography, high-speed encoding, large memory capacity, huge databases, and more complex semi-autonomous logic operations as well as software. The Sandia laboratory also has some innovations in neural operators, minimizing manual software parameters, and increasing the functionality of math semi-automated algorithms in complex visual and other application problems. Some calculations and observations I have made also provide some clue. In fact, today, sophisticated digital neural networks, complex block algorithms, databases, sensory systems, and AI accelerators have much in common with the several parameters of the amoeba. It's known from many scientific studies that the amoeba can be reoriented to a certain position by changing the external stimuli. Moreover, with a minimal receptor apparatus and 6 types of simple cells, the amoeba can briefly memorize an external stimulus if it's not distracted. The study 2013 years, so authored by Leon Chua, confirms the presence of minimal adaptive behavior in amoeba. In addition to the problems of modeling nervous system activity with the modern algorithmic methods, there is long-standing problems aimed at modeling the neural functionality of the flatworm. Such projects were launched in the wake of FAUN's 919s in different countries. The famous OpenWorm project, trying to model nematode neurons, also fails because numerical and algorithmic approaches are used. Unfortunately, many projects related to modeling brain activity, such as the Human Brain Project, and many others fail when trying to use modern digital technologies. Moreover, some engineers and scientists involved in these projects voluntarily admit to using erroneous approaches when creating machine intelligence. Given all the existing problems in the digital environment, it's clear that even decentralized cloud computing at the Department of Defense and complexly integrated transistor sensory technology at Aerobus company will not bring potential results. Well, let's get to the interesting part. Many scientists, programmers, and engineers in the field of electronics sometimes make analogies with the human brain, comparing it to the digital supercomputers, accelerators, or spike architectures. Unfortunately, the underestimation of many aspects of the complex nervous system leads to a profound misunderstanding of brain functionality, and to that end, approach to modeling it using digital technologies. In a real biological system, the brain not only morphogenetically rearranges itself throughout the life of an organism, but also adaptively self-organizes in the process of making complex decisions. In addition, a single neuron in some limits have more than 1 million synaptic connections, not tens of thousands, as described by many engineers and programmers. And an additional misconception is that organic memory has a specific address or cell. Such technical concepts do not exist in biology. Cellular memory is a system of connection and circulation of analog signal between receptors and the vesicle complex. Autonomous self-organization of the cellular communication system and local electrobiochemical reinforcement are the main mechanisms for the possession of personal goal-directed behavior. Purposeful behavior can only arise in self-organizing systems. Let me remind you that the principle of self-organization, which is the basis of cybernetics and synergetics, were described in detail by Alexander Bogdanov in 3 volumes of technology back in the early 20th century. Any biological organism requires certain energy expenditures for synthesis of something. Most of the energy is concentrated in the mechanisms of synthesis of synaptic vesicles in the Golgi apparatus. A single vesicle can contain at least 600 variables that encode, divide, and reconfigure several connections. This vast number of variables with each synapse makes the nervous system unpredictable when making decisions. Experimental evidence of the complex biochemical composition with the synaptic terminals was discovered in 1990s when radionuclide markers that could work with vesicular transporters first became available. The simultaneous coexistence of different types of neurotransmitters and neuropeptides imposed serious limitations, not only on electronic modeling of such processes but also on neurobiological study of signal mechanisms. Comprehensive approaches to detailed study of such neurobiological problems are practically not existent in any laboratory to date. Although this important and energy-consuming server process is the key to development of real artificial intelligence. Neurons basically have direct connections with other cells. Tweaking a single input signal can radically change the several parameterization of the output given the incredible huge number of biochemical parameters. Server architecture is relevant to dissipative systems and non-Markovan process. At the bottom of the slide is an illustration of circle of Willis, which energetically supplies different parts of the brain. This illustration is taken from Boris Hind's Atlas of Arteries and Veins. This example shows the variability of the circle of Willis that belonged to 2 different people who lived in 19th century. The bottom dense Willis circle belongs to the professor of mathematics Pavel Nekrasov, and the top wanted the usual Kuchman. As can be seen, even the energy supply of the human brain is an individual variable system. In fact, neurons are huge analog databases with accumulated sensory experiments that are autonomously reconfigured by physical connections. Diverse analog information blocks are continuously self-organizing, being in the state of chaos while centering a localized system of several connections in this thinking process. Local stimulation or more precise associative reinforcement occurs both externally and within the limbic system through the synthesis of the electrobiochemical opioid complex stimulating synaptogenesis and accordingly the self-organization of several connections. From the resulting experiments of traumatization and many years of city architectonic studies conducted in Germany and the Soviet Union during the World Wars, it became known that the complex associative thinking originates in the inferior frontal gyrus. It's the human orbifrontal cortex that is the basis of creating decision-making associated with the synthesis of completely new information. Autonomous integration of innate instincts of the limbic system, accumulated associative and sensory experiments, triggers reinforcement of self-organization mechanisms with the framework of goal setting. Now it's time to directly compare a biological system with digital technology. Here I compare a common coleopter beetle with the minimal associative behavior with modern microprocessors. The first thing to note is that the energy costs and energy source are very different. The coding process is also too variable. It's clear that biological organisms have time-varying analog multimodal signal encoding in contrast to digital technologies. Discrete signal even in the presence of high speed of operations, frequency, and processing power has serious disadvantages with energy cost and time complexity of algorithms. Binary encoding of transistor complicates not only separated logical architecture of microprocessor but also the manual syntax of program code and mathematical operation of algorithms. At the same time, the rigid programming architecture of computer printed circuit boards complicates the functionality of various operations, including chipset availability and writing drivers for peripheral devices. Two of these modern CMOS transistors, given the above limitations, cannot generate new informational signals. Generation of algorithms is only arithmetic and matrix operations of various registers and graphic processors at the level of logic or description, not changing the physical properties of transistors. They think with dielectric wear of the floating gate of transistors storing charge as a bit signal creates a number of problems, with a current leakage and overall power dissipation. The static architecture, materials of microelectronics, and its inability to reconfigure makes it impossible to come close to modeling even the single biological neuron. With such primitive logic of computers based on binary elements, modern data processing is energy-intensive, deterministic, and incapable of synthesizing completely new information. As for stagnation, the overwhelming number of current AI organizations are trying to keep up with the commercialization, advertising, hype, and financial returns of their own products. Because of the trend in microelectronics and software products for AI models, there is very rigid semiconductor paradigm. None of the companies still have real properties of adaptability in their own software products, and are now trying to change the paradigm of modern microelectronics. Increasing the number of transistors, frequency, and mathematical operations in microprocessors has nothing to do with artificial intelligence. The development of AI software products are an easier solution to attract more finance in many companies. Fancy names such as quantum, optical, or neuromorphic computing are just a screen for the rich commercial public, especially for investors who have no idea about the functionality of these technologies. The more the buzzword pop up, the more financial revenues flow in this field, and this problem does only apply to AI technologies. The transistor has free terminal nanodevice, but its decision is rather complex and poorly scalable. Most importantly, the transistor material, however innovative it may be, uses electron physics, and thus has very low structural unit of matter. This structure and physical processes of materials are very limited in logic functions, and consequently has poor performance. As stated by Department of Energy, approximately 15% of all resources are spent on electron transfer with transistor microprocessors. In addition to the lack of autonomous adaptive physics in transistor circuits, the weak current, which leads to complete degradation of materials. The smaller the dielectric wear of floating gates, the more problems arise. It's known from certain scientific studies that transistor materials have serious problems at nanoscale dimensions. When optimized transistors can even have sensing as well as analogous properties depending on the oxide material used, but again, these are limited in functionality and poorly scalable. In addition, transistor microelectronics is very easy to disable by microwave and radiation weapons, making them completely unsuitable for military and space programs. Adaptive oxide based on lithium-ion activity rather than oxygen has certain advantages in functionality and durability, as there is no defect associated with electroforming in this material. Memristor material, especially such as ruthenium-based molecular aromatic ligand, which can have up to 16,500 states, make them incredibly efficient and the adaptive devices in different applications. In addition to inbuilt capacitance and memory, the physics of the material has a mechanism for switching these properties mimicking a neuristor. The functionality of the unique molecular device from India surpasses even complex adaptive oxides in many ways. One such memristor can replace about 200,000 transistors by the number of simple arithmetic operations on the chip. In terms of built-in processing and memory functionality, such a device can replace the entire component of modern computer system unit, with one chip minimize the number of cable connections. The unique characteristic of the molecular memristor solve the problems of the chip scaling and complex functionality, thus making it suitable for modeling real machine intelligence. As for ML models at the level of digital technologies, they are equipped with phenatology. Phenatology is a well-known science that studies pathological processes after death of other organisms, when metabolic and electrobiochemical activity has completely stopped. After that, the structure of several connections is preserved, which evolved throughout the life of the organism, and the information content is destroyed. In this phenomenon, and that applies to the functionality of transistor microprocessors, constant semi-manual control over algorithmic operations is required, just as with the brain. Adaptively and autonomously, these technologies will not be able to work even if the mathematics of the algorithms becomes as complex as possible. The well-known neuromorphic computer from Intel company also has serious limitations on the property of adaptability. To confirm the dead activity of transistor, you can perform an easy experiment. Perform an autopsy on dead organism, such as a large hard-winged beetle. Remove the brain and place the dead tissue in fixative preparation. Using a signal-generator clamp, actuator probe, and mechanical micromanipulator, you'll be able to verify that there is minimal variability in the signal of the tissue. Since there are no morphogenesis in that nervous system, that is no complex reconfiguration of connections and biochemistry, this activity is static. The modern static microprocessors of supercomputers have the same analogy. Continuous algorithmic and mathematical manual external micromanipulations are required to automate complex and unforeseen processes, not to mention the high energy consumption of primitive transistor CMOS electronics. The suppression of any advanced technology, much less the introduction of new computer architecture, is not new news in a tough business environment. Beyond commercialization, there is a big trend and hype. Even 19% of university programs and startups are focused on the established trend and science. At the moment, advanced AI software models based on transistor are a hot topic in almost every field of science. In such a situation where there is high demand and revenue from primitive computer architecture, it is guaranteed that no company will try to change the paradigm of modern computing. National organizations and research agencies, especially in the field of scientific and military units, where the new creative approaches are required, are very interested in new computer architecture. Many national organizations that are interested in advancing computing technologies are trying to fund, at least minimally and for a short period, the development of memoristic technology. For these reasons, memories are still not integrated into modern digital technologies. Let's hear what Richard Stanley Williams thinks about wise allocation of investment portfolios when some organizations try to implement memoristic technologies.
One of the things that we have a problem with in the commercial world is that we have to disguise any revolutionary advances that we make as evolutionary, because customers get scared if they think that they have to abandon everything that they've ever done, right? So if we came out tomorrow with a brand new computer that had brain-like computation, no one would buy it. Or maybe a couple of research labs someplace, but no one would buy it because everyone would be so afraid of it, and they'd be thinking that they've got to all of the they'd be thinking about all the programming that they'd have to do in order to make in order to be able to use it. So we need we essentially need to introduce these types of ideas gradually and literally make a new accelerator that we would use in on a chip be something that you can just call with a simple statement in a normal C-type program. Okay, and there's all sorts of fads and bandwagons that are out there where people that are just sucking way too much research funding. I mean, there's so much, graphene. I mean, please give me a break. Deep learning. Everybody in the world seems to have jumped on these bandwagons, and so with all the money that's getting spent on that, frankly, the advances that are being made are very, very incremental. Whereas if governmental funding agencies would do the same thing as investors and understand that you don't throw all of your money on some very wild speculative investment, but you try to sort of broaden your portfolio out. I mean, that's how you actually get rich, is by having a reasoned portfolio where you spread risk and reward over a wide area. And so that's where we need this investment portfolio.
Despite all attempts to suppress the realization of new memristor as well as new resistor microelectronics, there are some attempts to test and even implement this technology privately. The famous Moscow Institute of Physics and Technology is trying to apply the first new resistor computer based on new oxide materials in solving complex problems. The United States National Microelectronics Research Strategy has also confirmed the provision of memristor microelectronics development in the field of AI technology. Nevertheless, China has already integrated the first memristor chip on a small commercial scale. At the Technical University of Dresden, they unconventionally integrated commercial XN.O memristor chip with standard semiconductor components on a printed circuit board to produce a semi-adaptive neuristor emulator. An interdisciplinary program from India aimed at detailed study of new aromatic molecular memristor has developed a unique parallel adder that has no analogies. It's time to talk about the application of neuristor ionotronics. Since our neuristor consists of memristors and memcapacitors, it uses the physics of ions rather than electrons. Such a technology is called ionotronics. First, it should be said that such an advanced technology of real machine intelligence is in demand in the field of Ministry of Defense. In addition, most of the funding for this technology comes from the Air Force Office of Scientific Research and the Air Force research laboratories. In the defense domain, such a computing system is very effectively used in the field of cybersecurity, military robotics, and adaptive aviation. Now, neuroionitronics has a narrow but applied application to solve very serious problems. Some developments in the field of neuroionitronics are well classified. It's quite likely that in a few decades, such an adaptive system will be used on more global scale for a new generation of military equipment. In this slide, I would like to show one of a rare and unique experimental study on heuristic technology within a military memory program. The research work is led by Young Chen, who is Professor of Mechanical Engineering, Material Science, and head of the Intelligence Nanosystem Laboratory. The short video shows a comparison of the adaptive behavior of the drone with the other counter system under changing conditions. There are approximately 400 oxide sensors and 20 neuristors arranged in the chip. A sensor nano device is similar to a transistor, but has different structure and physical process. A single sensor combines analogous sensor processing, memory, and warning functions simultaneously. By doing so, the drone adapts very quickly compared to a digital computer architecture. And so, let's look at the results. As you can see, the heuristic computer architecture handles the primitive task of returning to target position better than the operator, and adaptive digital proportional integral derivative controller, PID controller. Another problem associated with CMOS electronics concerns its physical properties and the structural electronic unit of the semiconductor material. As I said, modern electronics are not difficult to disable by moving them into a displaced radiation environment. However, more advanced electromagnetic military technologies can destroy many other electronic components. The hypersensitivity of electronics to microwaves is related to the problem of electron hole physics within transistor components. For example, when exposed to powerful microwave radiation on a modern telephone, the electrons of the semiconductor components are removed or shifted from their original position, causing the electronics to malfunction. Even water has a very detrimental effect on digital electronics. Salt ions dissolved in water and various impurities that act as conductor create short-circuit damaging electronic components. In addition, modern digital electronics is very fast technology to deal with cyber attacks. Any failure of electronics leads to a complete failure of cyber warfare and disruption of communication system, as we know from the practice of most countries. Let's recall the microwave weapons test demonstrated by Boeing Corporation in 2012. Given the significant progress in the field of electromagnetic weapons in some countries, it has begun to be realized that modern digital electronics can solve the issue of power consumption, interrupted operation, and data protection. For this reason, the Ministry of Defense is intensively funding the development of another computer architecture.
Though we can't show actual images of the CHAMP or Counter-Electronics High-Powered Microwave Advanced Missile Project, this animation shows a simulated weapon flying over selected targets, hitting them with high-power radio wave bursts and defeating their electrical and data systems without causing injury or collateral damage. But it was no simulation Tuesday over the Utah Test and Training Range, where Boeing and the U.S. Air Force Research Laboratory's Directed Energy Directorate successfully flew the first fully operational CHAMP weapon.
We hit every target we wanted to. We prosecuted everyone. Today we made science fiction science fact.
This video, recorded during an earlier test, shows what CHAMP is capable of. Watch the computer screens in this office as the directed energy hits the building. While the computers were knocked out, there is no structural damage. Fade to black.
When that computer went out, when we fired, it actually took out the cameras as well. We took out everything on that. It was fantastic.
Excellent team. I mean, like I said, the reason we are successful is due to the team and the team effort.
A non-lethal weapon that can defeat targets without collateral damage is an idea that's been portrayed in television and film for decades. But this, says AFRL CHAMP lead test engineer Peter Finlay, is no movie.
We're not quite up to the place where the Star Trek and Star Wars movies are, but this is definitely an advancement in technology to be able to give us an opportunity to do things that we couldn't do before.
James Dodd, Vice President of Advanced Boeing Military Aircraft, says his team is focused on developing the innovation to protect U.S. troops.
We know this has some capabilities and some impact. And so we're really trying to engage the customer and see if there's a way that we could actually get this fielded and implemented sooner than later.
After its first flight, the Champ missile flew to an undisclosed location on the test range, and the flight was intentionally terminated. Boeing and AFRL teams are now analyzing the data and telemetry from this flight, which not only made history, but stands to change it as well.
And so now let's talk about the actual use of memoristic technologies that work in incognito mode for defense purposes. Memoristic computer architecture, as well as analogy memory, has recently been effectively applied in the field of complex network system analysis and optimization, as well as cybersecurity and even hacking. Another application where analogy memoristic computing is used is military aviation. The high adaptability, autonomy, and multifunctionality of sensory system of unmanned drones is a key area in air defense. Moreover, analogy cryptography and memoristic-based blockchain technology effectively address the challenges in cybersecurity, complex signal encryption, and adaptive memory in large databases. The development and application of new computer architecture in military fields demonstrates an effective solution to the main problems of the Ministry of Defense of large countries. Alright, let's move on to a newer topic. All current problems of digital AI models are related to the fact that they lack internal goal setting and its partial reinforcement. And this is a very challenging process in terms of neurosystem activity. Goal-directed behavior, which is not related to the solution of specific tasks, is the result of mobilization of autonomous mechanisms for self-organization of several structures from a state of chaos. That different information blocks with multi-direction signals are distributed, modulated, shifted, and converged in certain server connections. The process of self-organization can be clearly seen in the accelerated footage of blastula and cell pattern formation in the embryonic stage. As can be seen from accelerated footage, in the state of chaos, autonomous mechanisms of accelerators and inhibitors with after-catalytic long-range reaction from a complex pattern. The neocortex, which is associative superstructure of the limbic system, plays an important role in decision-making. However, if the innate instinctive behavior of the limbic system doesn't match the associative behavior of the limbic system, goal setting may not occur. The duality of consciousness of the human brain makes it possible to make great efforts in certain direction if it is favorable for the organism. The hardware basis for the realization of such properties already exist. Several nonlinear networks, CNN, is a memoristic model of a universal machine that can form a self-organizing pattern when solving the most complex tasks. At the hardware level, autonomous programming of memoristic circuits can be realized by a device having an adaptive sensing system, short-term embedded memory, and signal generation. Is nearest several nonlinear networks that can cope with the solution of very non-standard tasks that are beyond the power of supercomputers and even the human brain. The first attempt to create an electronic version of nonlinear several networks belonged to Luan Chua. Then, Toshiba company used this model in certain photosensors. On this slide, I show my concept of a possible future in the field of encryption systems. It is likely that if heuristic-based several nonlinear networks find more extensive applications, it is likely that the intermediate device will need to encode signals in a highly complex way. Today, there is decent research work related to data encryption using an array of memristors. In addition to random number generation methods, there is another approach. Multilevel attractors with nonlinear mathematical equations, electronic circuits, and memristors can simulate supercomplex modulation and consequently stochastic encryption of informational signals. Unfortunately, such approaches have been applied very rarely and in very narrow domains. Most importantly, such a peripheral device can act as a mechanism for reconfiguring links and then generating new signals in a separate heuristic chip. Such a data encoding architecture could eliminate the need for current close-based digital encryption methods. At this point, I would like to describe my new concept about CNN technology. If similar properties are realized in future heuristic-based computing systems, they will be dramatically different from current AI models and even more so from large AI services. To begin with, we need to design heuristic circuits to get rid of side elements using the latest advances in electron beam lithography and material science. The functions of molecular as aromatic memristor and memory capacitor in one component are our best technology solution. In this way, it will be possible to model a neuristor in a single device. With compactly packaged molecular neuristors on a chip, it will be possible to partition each dedicated neuristor server into clusters. Each CNN unit for a local user as a minimum should have an attractor encryption system and mechanism for reconfiguring the neuristor network, thereby maximizing the thinking capabilities of the first blade server. The first blade server contains CNN clusters. For local network members, we have the intelligence of a large insect with minimal computational resources. This is necessary for fast instinctive decision-making in the presence of multi-sensor input and output. A second blade server containing large CNN clusters should mimic the intelligence of self-put octopus with internal goal setting and voluminous computational resources. If necessary, it will be possible to activate the reverse semi-autonomous access between the first and second blade servers for important tasks selected from the user clusters of the first blade. If the first blade server with insect intelligence is unable to solve the partitionable task, the request will be automatically forwarded to the second blade server. Selected non-standard problems can be solved privately and then issued with the resulting answer. In addition, if the requests sent by users are less relevant to intelligence blade server with self-put intelligence, it will reject them in private mode. Also, feedback from the second blade server to the users of the first blade server is needed to clarify the question asked and possible approach to the problem solving by the CNN users. In this way, it's possible to analyze more accurately the quality and intelligence of the participants by brain energy expenditure given the detailed cytoarchitectonics database. Such an intelligence analysis of users can help to select very capable participants in government, scientific, and many other programs. The count of insect and octopus intelligence mechanism for partial reinforcement and inhibition of analogy blade server processes must necessarily be present. With missing information in solving complex problems, network access to large databases based on molecular memristors with analogy addressable memory can be activated. A neurocomputer or a cybernetic organism with sufficiently large computing resources may become a new paradigm in the field of military tactics in the near future. Such adaptive computing systems require new types of programming and new personnel. By changing the functional specialization of the neural system based on neuristor circuits, it's possible to specify a unique computer behavior or properties not found in biological system. Pre-trained and given access to large databases, neuristor organisms will start to act very quickly and independently. It's quite possible that such ultra-advanced technology will in the future eliminate the need to use modern software methods for cyber attacks and modern types of weaponry. Given the very high speed of encoding analogy signals and autonomous mechanism of reconfiguration of the neuristor circuit network, the biocomputer will be able to create new weapon principles and technology solutions that are likely to be a hit of the current century. And the country that develops such a neuristor-based cybernetic organism is likely to become a leader in the future military capabilities. As a simple solution, it would not be difficult to integrate a neurocomputer into modern digital systems by pre-training it with the help of experienced personnel. This is not the case with current AI model accelerated technology. In practice, two small devices would be able to perform both sensory and peripheral nervous system functions, providing complete autonomy in digital environment. Taking control of servers, sensors, and local computers and targeting behavior with information resources could be a major game changer in many workplaces. An integrated general-purpose adaptive neurocomputer will be able to solve any problem in real time with the rules of a particular company. What is considered the most interesting part of this presentation? It's well known that cybernetic principles are sometimes used in solving very complex computation problems in economic and public administration. Cybernetics generally postulate external algorithm control, storage, self-organization, information transformation, and feedback. It's very interesting science, but unfortunately, it lacks adaptive goal-directed behavior with built-in periodical reinforcement. A system that has more analogy properties can be called adaptanetics. It has several nonlinear networks and several automata based on heuristic computation that could be the fundamental paradigm for the future state control mechanism. Instead of selecting capable individuals for top positions by the technology of cerebral volume analysis, a better solution will be to have and change the functional specialization of the nervous system. Variability of the volume and functional zones of neuristic clusters in the state system can radically change the principle of search management. Feedback provided by private or official individuals will be processed in the computational system of adaptanetics. In this case, adaptanetics is a sensor system, local computers, edge devices, and self-organized CNN network of neuristic-based supercomputers. Controlling adaptanetics will be an extremely challenging task. Control will require radically new knowledge of dissipative science and correspondingly new type of people. First of all, an external software system for modeling self-organization mechanisms must be developed for local actors in adaptanetics as an approximation and extrapolation of their own ideas. Such digital technology will be needed to predict global or local consequences in the adaptanetics system. If the legislative or scientific ideas and their forms of implementation lead to disorganization, neuristic adaptanetics will quickly find the causes of the problem and replace them with its own solution. Otherwise, if a local participant will maliciously inhibit certain processes in the system of self-organized adaptanetics, the mechanism of network blocking and elimination of the participant will be activated. Given the external and internal multi-level complex analogy encryption, such a system will be extremely difficult to crack. The activity will be similar to the behavior of self-preservation instinct of a reasonable organism, as well as local participants, residents of the state should also have network feedback to adaptanetics to identify and describe local or search to problems. In addition, adaptanetics will have links to large databases in different scientific departments. If adaptanetics can solve the problem of creating a universal energy system on its own, it will fundamentally change the unit of measurement of the cost of producing goods and products. The production and value of each product will be measured in energy costs, not bitcoins or monetary currency. An innovative invariant price list based on a universal energy source in an economic system that can generate virtually infinite amounts of energy will have a potential advantage over other countries. Adaptanetics, as a complex adaptive computing system, can be approved and put into production only if there is political will among the leaders of certain countries. As I said in the previous slides, the functional specialization of neuristic bioprocessor will be required to realize the high intelligence capabilities of the new computing technology. This means that for each ultra-large neuristor integrated circuit, analogy and lithographic programming of the heterogeneous packing of memristor elements and their interconnections with each other is required. The variable architecture and functionality of the memristor elements within the biomorphic processor will allow control of the type of neurosystem depending on external and internal sensory stimuli and responses. And this is a very important point, as this type of adapter architecture is practically not considered in any laboratory. If you supply a controlled bioprocessor architecture to any robotics, it will become completely elusive and unpredictable in terms of behavior. To produce the properties of predatory, fast, and at the same time very intelligent organism, it is necessary to integrate different types of neurosystem. Combining the functions of the alligator's midbrain, the owl's optic tectum, the mushroom bodies of Coleoptera, the autonomy of the peripheral ganglia and octopus tentacles, the receptivity of electric fish, and the associative zones of the human brain are the unique structural unit of a new bioprocessor. In neurobiology, such integration parameters can be realized only using neuronal transplantation of brain sections from different animals. This surgical process is very labor-intensive and limited in reproducibility. Dynamic reconfiguration of functional zones of the neuristor array, roughly analogous to the mechanisms of external embryonic positional signaling, will give the bioprocessor more adaptive integrative properties. Given the strong manufacturing potential of electronic lithography in the field of microelectronics, a simple solution will be to realize the integrative properties of neuristor-based bioprocessor. Adaptive regulation over the bioprocessor will be possible using a hardware-enunciate medium including external and internal position encoding pulse signals. Locally programmable excitation and inhibition pulses of analogy neuristor circuits will allow changing the activity of the bioprocessor and more precisely control its purposeful behavior. It's also important to provide limited network access for the bioprocessor to external computer environment. Because an advanced neuristic biocomputer will have enormous adaptive properties in contrast to modern electronics and digital AI models, it is not excluded that serious negative consequences may arise. To ensure complete security, it is essential to have a multi-level ban of third-party computational sources. By implementing bioprocessors along the lines of computing servers as large-scale system, one does not have to worry about energy costs. If we increase the number of neuristic bioprocessors to 100,000, the energy consumption will be equal to the power consumption of a discharge lamp. Along with the computational potential of memoristic ionotronics, there is the problem of commercialization. It's widely known that any cable connector or semiconductor component of electronics is not durable and over time begins to undergo gradual oxidation and degradation under the influence of external conditions. The presence of oxide layers in modern transistor circuits, SMD capacitors, and other elements creates several limitations and makes modern electronic architecture very primitive. The problem with the commercialization of memristors and memcapacitors is the presence of mechanism of ionic filament electroforming with the oxide material and the uncontrolled stochastic behavior. The problem is mainly the diffusion or migration of oxygen ions with the device. The drawbacks include that oxygen from the environment penetrates into the zonal site cavities of the oxide materials, leading to the diffusion of ions within the device. Such physics of oxide materials gradually destroys the potential of the memristor component. This slide indicates a small list of oxides that have disadvantages. However, there are alternatives to oxide materials. Single crystals like lithium niobate do not require electroforming and utilize uniform diffusion of lithium ions rather than oxygen ions. The resistive state of the memristor device can be precisely controlled. In same concerns and commercial chalcogenides that locally used in some electronic components. XN.O, a non-profit company, produces memristor chips as a sample and mainly for research purposes. Otherwise, such a memristor chip requires additional electronic components to emulate complex sensory and stochastic behavior. To date, there is only one single innovative non-oxide material in terms of enhanced adaptability, multifunctionality, energy independence, durability, and reproducibility. Ruthenium-based molecular aromatic memristor is the best candidate for the development of real analogy artificial intelligence. Researchers at the Indian Institute of Science have already developed a prototype biocomputer based on a molecular processor that stores and processes over 16,000 states. The molecular memristor bioprocessor is a hit of all modern digital systems, including the latest graphical processors, in terms of functionality, speed, and adaptability. In addition, detailed research is underway in international laboratories to improve the performance of this molecular metal organic device. The molecular memristor component is almost ready for commercialization and being considered by certain international companies. Numerous conferences dedicated to the topic of the molecular device at the Center for Nanoscience and Engineering indicate that this innovation is ready for commercial release. In terms of having a strategic advantage in the counter in the field of new computing technology, it would be nice to have our own research and production association. As it became clear, the development of neuristor will require two types of memristor components and a non-standard software operating system. The synthesis of the memristor material will require sophisticated lithographic, microscopic, and spectroscopic techniques, and a set of measuring instruments can be added to the list. Moreover, a secondary source will be needed for detailed analysis of molecular and oxide materials. Such a technological set in the Research and Production Association will be needed to reduce the time for research and development. Moreover, the synchrotron will have many other different applications. However, there will be independence on imports of complex oxide and molecular materials from countries rich in natural resources. Considering all financial costs, including the commercialization of the neuristic biocomputer, the total budget can be more than $1.5 billion. There is another way to reduce the investment portfolio or initial capital by orders of magnitude. It is possible to use the existing independent resources of some companies to create a virtual organization. If you use off-the-shelf memristor chips produced by commercial and non-commercial companies, as well as scientific programs of research foundations, there may be some limitations. The disadvantages of such off-the-shelf products include static material functionality, architecture, and application. Neuristor modeling will require large-scale electronic printed circuit board dimensions and standard semiconductor components. This computational architecture lacks high adaptability, autonomy, and multifunctionality. The energy-intensive decision of a semi-memristor biprocessor may be suitable for research purposes as an emulator, but not for serious tasks. In addition, modern semiconductor components are not durable and can fail quickly. Due to the above-mentioned problems, ready-made memristor chips are practically not suitable for wide commercial applications. Molecular memristor from India have a huge commercial potential, as they can cope with very serious problems. Firstly, the aromatic memristor has ultra-adaptive physical processes with the materials, and also has no oxide impurities, which makes such a device durable and productive. By investing an acceptable initial capital in the development of biocomputer based on molecular chips, it is impossible to maximize financial returns in sales by applying such advanced technology in various fields. Neuroscience microprocessors with unique parameters will help to solve not only the problems of cybernetics, defense ministry, and robotics, but also to eliminate the whole additional set of digital devices. Using innovative neuromorphic technology, we eliminate the need for advanced power supply systems, server cooling, fire suppression, and uninterruptible power supply. The miniaturized biocomputer will not require large premises and complex cabling. Now let's listen to some video fragments of very interesting neurobiologist, neuromorphologist, and evolutionist. Sergei Savelov, as an emeritus professor and doctor of biological science, gives a rather sober opinion on the current models of artificial intelligence and the new architecture of electronics. I believe that some AI engineers and developers will be interested in how new adaptive computing systems should look like.
I am constantly asked if it is possible to create a biosimilar neuristor. Yes, this can be done. First of all, it must have a system of connections between other neuristors. Secondly, he must break and form new contacts randomly. In addition to transmitting signals that are used in primitive neural networks, the neuristor must slow down and interrupt information signals. Thirdly, the neuristor must perceive and sum the signals. Fourth, the neuristor must have its own variable dynamic memory. Biological neurons have such a memory. But this memory is not chemical but circulates through synaptic contacts to the cell body and back. Next, the neuristor must generate completely new signals. Such functions are not considered in the field of computer technology. The most important property that a neuristor should have is self-destruction and resurrection. The brain has this property in the process of solving problems. The eighth point is the nonlinear processing of the opposite signals of the neuristors. And finally, a single neuristor must obey the systemic interests of a large group of neuristors. To build a model of the brain of an artificial animal, other principles of work are undoubtedly required. I've been working on this problem for a bit. In order to build at least the nervous system of a simple artificial worm, you need to create properties that are not considered in any computer system. Goal-setting programming makes any computing system meaningless. An artificial animal should receive gradient pleasure. Not having reached the final result, the nervous system should receive pleasure. Try to program such a process if at all possible. The next point is the autonomous regulation of the energy consumption of the nervous system depending on the load. And the last point is the ability of the nervous system to sacrifice energy and structure in the framework of goal setting. But after the implementation of such processes, inevitable consequences will occur. The artificial nervous system will become uncontrollable. I have spoken about this topic many times. A video has been published on the publisher's website in which I discuss the topic of an artificial animal with the famous Olympiad champion in programming, Andrei Lopatin. Unfortunately, such a system cannot be pre-calculated mathematically. Requires direct simulation of new electronics and programming.
That is, the command electrical signal is transmitted through neurons, but important meaningful information is missing. It turned out that this whole system works well only with muscles, which has been known since the time of Ivan Mikhailovich Sechenov. However, over time, it turned out that the signal is transmitted really well with the help of amplitude, frequency, and transmission rate, but unfortunately, this signal does not contain the information that the researchers expected. Now let's move on to the most key point related to crypto encryption. The human brain is a giant crypto encryption machine. On what principles does this system work? Such a crypto encryption machine is based on the fact that the signal that Eccles discovered and then was confirmed by many graduate students and doctoral students really exists and is transmitted through a membrane as described in many textbooks. However, most importantly, during signal transmission, most of the processes occur in a chemical synapse. Why? With each transmission of a signal, a sufficiently large number of synaptic vesicles are ejected. Inside each synaptic vesicle, there are a huge number of different neurotransmitters, from 20 to 26 types in different combinations. Each synaptic vesicle that reaches the membrane ejects a mixture of different neurotransmitters and in different proportions, since a huge number of synaptic vesicles are ejected in one chemical synapse. This is the crypto encryption process. Signals run through the neuron, which contain all the information, and at the time of signal transmission through biochemical synapses, they are encrypted. What is the reason for the encryption process in signal transmission? This process is built into the function of a chemical synapse and exists in order to separate information flows within one neuron. This mechanism does not exist in order to hide the signal from some professional hacker. With the help of such crypto encryption, that is, an extremely complex signal coding for modern mathematics and computer technology, a neuron simply transmits a signal. That is why this problem is one of the key ones in the construction of models of artificial intelligence that could imitate the work of the central nervous system as closely as possible.
The reptiles we talked about today are basically just instinctive hormonal answers to questions. And what? Their system, which developed in reptiles, was quite complex, but it is built on what we now call the limbic system, that is, instinctive hormonal regulation of behavior. If I could find people who know how to do something, I mean build neurocomputers, then of course, a neurocomputer should be built according to the reptilian principle, and completely changing the architecture and logic of modern electronic computers. Here, they just gave the maximum result, but I think this will never happen, because the inertia and paradigm that exists now in robotics, it will not allow us to do anything advanced in the next 10 to 15 years.
In many advanced countries, there are no less impressive achievements that are associated with the construction of an artificial brain. Given these ideas, scientists in many countries began to study those same synapses. Typically, most engineers don't even have a basic understanding of how these synapses form and break. In addition, most scientists are trying to create synapses using mathematical and software methods based on binary code and Boolean algebra. As you understand, such projects are complete idiocy. Unfortunately, most engineers do not know that there are approximately 600 to 700 types of modified signals transmitted through a single synapse, and they depend on different types and combinations of neurotransmitters. Thus, natural scientists increase their own passion through a lack of knowledge. For this reason, scientists are trying to create a complex synapse since they cannot make it morphogenetic so that it can assemble and disassemble. Researchers at Stanford University have developed a 3-electrode water salt-based transistor that has 500 non-volatile states. I don't know about states, but the fact that the information transition will be rather doubtful through such an artificial synapse is worrying. Although at the University of Arkansas, progress is moving even faster. Engineers have developed a neuromorphic chip that can remember previous signals when repeated. This is certainly a brilliant achievement. However, this technology has serious limitations. The memristive element is again solid state and has a complex design, not to mention the fact that it cannot be assembled and disassembled. That is, the benefit of such an electronic component is not very high. Thus, modern research shows that, unfortunately, money and strong-willed efforts have little effect on the result if it is possible to report in such ways. Let's hope that some more meaningful projects will find support. Because at the moment, funds are allocated exclusively to popular research. Such research includes today's digital dendrites and electrolyte-based artificial synapses. The initial futility of these claims and technologies is pretty clear. However, let's hope that sanity will find its support and that budgetary funds will no longer be wasted.
As you can see, neuroscientist Sergei Yagubov is also focusing on the creation of countermechanisms in the development of non-semiconductor technology of neuromorphic intelligence into account its adaptive and speed properties. Based on his own embryological research, Sergei Yagubov has a deep understanding of what mechanisms are required to control the purposeful behavior of artificial intelligence, and this opinion is worth wishing to carry free. In conclusion, we would like to note that with the help of neuroscience intelligence, it's quite possible to open many Pandora boxes in different scientific fields. The potential results obtained by next-generation biocomputer will likely be centuries ahead of all existing human technologies, knowledge, and ideas. Having given the green light to date, such a strategic advantage can only be realized on a private or commercial level. I believe that very interested parties, with the framework of serious governmental, economic, technological, and scientific progress, will contribute to the further development of the new adaptive computing system. I thank all those who listened to this presentation and for your time dedicated to the topic of developing real machine intelligence. Thank you and goodbye.